Today we are looking at the paper Turing Completeness of GNU Find Colin. From mkdir-assisted loops to standalone computation by Keigo Oka.
And if you are an engineer who thinks you know the find command, you're about to have your world turned upside down.
The headline here is just massive. The author proves that the standard GNU find utility, the thing we all use to locate files or clean up directories, is actually Turing complete. It is not just a search tool. It is a fully capable, albeit weird, computer.
Correct. And the paper provides 3 distinct proofs of this capability right up front. First, it uses find combined with a mkdir command to simulate a 2-tag system, utilizing directory paths as memory and regex for logic.
Second, and this is the one that uses a relatively new feature, is find entirely on its own. No mkdir at all. Just find simulating a 2-counter machine using the file 0 from flag.
And then third, the hard mode proof. Back to find plus mkdir, but stripping away the powerful regex back references, proving find can compute using just the directory structure itself as Boolean logic gates.
So basically, find is a weird machine that can technically run any algorithm a supercomputer can run. That is the core insight here. Welcome to AI Paper Podcasts, where we summarize the latest AI and tech papers for you. Let's get right into the details.
It is a pleasure to be here. This is one of those papers that really highlights the hidden complexity in our daily tools.
I have to admit, when I first saw the title, I thought it was a joke. I mean, find, really. It walks a file tree. I think of Turing Completeness as something for Python or C++, or maybe accidentally in things like Minecraft Redstone. But how do you get from walking a tree to universal computation?
It feels completely counterintuitive, doesn't it? But this actually fits into a long, proud tradition in computer science of discovering accidental computation. We have seen it with Sort, the stream editor. We have seen it with the move instruction in by 86 chips.
Oh, right. Someone proved you can do everything just with move.
Exactly. People have even proven that the blocking rules in Magic the Gathering are Turing complete.
So if you have the right deck of cards, you can calculate the Fibonacci sequence.
You really can. If a system has state, a way to loop, and conditional logic, it is a computer. And find has officially joined that club. The goal today is to break down exactly how you turn a file searcher into a processor. And it all starts with the most basic requirement of programming, which is the loop.
Right. This was my first technical hurdle when reading the paper, because find is designed to be a directed acyclic graph traverser, essentially. It starts at the top, goes down the list of files, and stops when it hits the bottom. That is a straight line. How do they force it to loop forever?
That is the fundamental problem. To compute anything, you need an infinite loop. You need to be able to go back to the start or just keep going indefinitely. The solution the author uses for the first proof, the mkdir proof, is essentially to build the track in front of the train while the train is moving.
I love that image. Building the track while the train is moving. How does that translate to a file system, though?
They use the mkdir command inside the find execution. Specifically, they use the execdir action. Now, strictly speaking, find uses pre-order traversal by default.
Meaning it visits a directory first and then looks at what is inside it.
Precisely. It walks into a room, looks around, and then processes the contents. But here's the hack. When find enters a directory, let's call it directory X, the script executes a command to create a new subdirectory inside X. Let's call that new one X/Y.
Okay, so it is inside X, and suddenly X/Y appears out of nowhere.
Right. And because find has not finished looking at X yet, it spots this brand new directory, says, oh, new content, and walks into it.
And once it is inside X/Y,
it triggers the command again, creating X/Y/Z. It effectively creates an infinite descent into a directory structure that literally did not exist when the program started.
It is like painting a hallway, but every time you take a step, you build another foot of hallway in front of you.
That is a perfect analogy. Now, there is a very nerdy but crucial detail here for the systems engineers listening. You have to use execdir, not just the standard exec flag.
Why does that distinction matter? Is it just a syntax thing?
No. It is about the resource model. If you used exec, find passes the full path of the file to the command. Eventually, that path string, X/X/X, would get so long it would hit the operating system limit, path max.
Ah, right. The buffer overflow. The hallway name gets too long to pronounce, and the kernel just kills the process.
Exactly. But execdir runs the command inside the current directory. It only cares about the local context. So the command just creates a folder named X inside the current folder. It does not care that it is 50,000 layers deep. It allows for infinite recursion within a finite file name length.
That is incredibly clever. It completely sidesteps the OS limitation by keeping everything local.
So, okay, we have an infinite loop, we have the engine running, but a loop is not a computer. A fan spins in a loop, but it doesn't do math.
Yeah.
We need data, we need state. In this first proof, using find and mkdir, how are they storing information?
They are simulating something called a two-tag system.
Refresh our memories on the two-tag system for a second.
Yep.
It is a computational model similar to a Turing machine, but a bit simpler in its rules. Imagine a word, just a string of characters. You read a symbol from the front of the word. Based on what that symbol is, you append a new set of symbols to the end of the word, and then you chop off the first two symbols.
So it is a queue, first in, first out, but the out changes what comes in.
Correct. It transforms a string over and over again. Now, in this find computer, where do you think this word is stored?
Well, based on what you said about the hallway, I am guessing the directory path itself.
Bingo. The file system is the tape. If your computation state is the word banana, you literally have a directory path that looks like b/a/n/a/n/a. The folder names are the data.
So we are standing in directory A, inside directory N, inside directory A. That is wild.
Yes. And to do the computation, to read the b at the start and add something to the end, they use regular expressions.
Find has a regex flag, right? I usually just use it to find files named .jpg or .log.
Right. But here they use regex back references. You know when you use parentheses in a regex to capture a match and then use \1 to refer to it later?
Yeah, it is like copy-paste.
Yeah.
Find this pattern, copy it, and paste it over here.
Exactly. They use that to read the current directory structure, which is the state, capture the part they need to keep, and then use the mkdir command to create the next segment of the path based on what they matched.
So the logic is essentially, if the path ends in A, make a directory named B.
And if the path ends at B, make a directory named C. The regex decides what directory gets created next, so the computer just keeps descending deeper into the folders, transforming the path string step by step.
That is surprisingly elegant. It halts if the regex doesn't match anymore, or it loops forever if the calculation doesn't finish.
It is elegant.
Yeah.
But the author of the paper, Kigo Oka, apparently felt this was too easy.
Too easy. Using infinite directory recursion and regex back references to build a Turing machine is too easy.
Well, computationally speaking, yes. The expert critique here is that regex with back references is actually extremely powerful on its own. Some computer scientists argue that if you're using back references, the regex engine is doing all the heavy lifting. You aren't really proving find is a computer, you're proving regex is a computer.
Ah, I see. It is like saying I built a car out of Legos, but the engine block is a real Ferrari engine hidden inside.
Exactly. So the author decided to prove find is Turing complete without mkit at all.
This is proof number 2, the standalone challenge. This is the one that really surprised me. If you cannot create directories, you cannot do the infinite hallway trick. How do you loop without creating depth?
This proof relies on a feature introduced in GNU Find version 4.9.0, released fairly recently in 2022. It is the files zero from flag.
File zero from, it sounds like a boring bureaucratic switch. What does that flag do normally?
Normally, it is for safety and batch processing. If you have a list of 1 million file names in a text file and you want Find to process them, you use file zero from. It tells Find to read the input list from a file stream instead of trying to cram them all onto the command line.
Okay, so Find is reading its to-do list from a file.
Here's the hack. Start Find reading from a file called S. While Find is running, use the svrt action, which allows Find to write to files to append a null character to file S.
Wait, it is reading from file S and writing to file S at the exact same time?
Yes. Find reads an entry, executes a command, and that command adds a new entry to the end of the list Find is currently reading.
It is like laying down railroad tracks while riding the train, but instead of directories, it is just bytes in a file.
Precisely. It never hits the end of file because it keeps pushing the end further away. It creates an infinite processing loop using a single flat file.
That feels almost illegal, like a violation of physics, or at least a violation of good coding practices.
It is definitely a violation of intended use. But it works. So now we have a loop again. But we have a bigger problem. Without mkdir, we cannot use the directory path as our memory tape. We cannot use the folder names to store the word banana.
Right, we just have a flat file now. How do we store numbers? How do we calculate anything?
The author simulates a two-counter machine. This is a theoretical computer proposed by Marvin Minsky. It is very simple. It just needs 2 registers, or counters, that can hold an integer. And you need to be able to do 3 things: increment the counter, decrement it, and jump if 0.
Okay, increment, decrement, jump. But how do you store the number 5 in a file search? Do you write the number 5 in a text file?
No, that would require parsing text, which is hard. They use unary encoding.
Unary encoding. That is caveman math, right?
Caveman math, tally marks. To store the number 5, you create a file containing 5 bytes. Or even simpler, 5 null characters.
So a big file is a big number and a small file is a small number.
Exactly. If the file size is 0 bytes, your counter is 0. If it is 10 bytes, your counter is 10.
Calculating must be tedious. How do you do +1?
You use fprintf to append 1 byte to the file. Boom, increment. The file is now 1 byte larger.
Okay, that is easy enough. What about -1?
That is trickier. You cannot just erase the last byte of a file easily with find. So you have to use the size check. You check, is this file at least 2 bytes big? If yes, you delete the whole file and create a new file that is 1 byte smaller.
That is so destructive. To subtract 1 from 100, you delete the number 100 and write the number 99 from scratch.
In this system, yes. It involves a temporary file to hold the new value, but the logic holds. It works.
What about the jump if 0? In programming, that is an if statement. If the counter is 0, go to line 50.
Find has logic operators. -O means OR. You check, is the file empty, represented by size 0. If it matches, you execute a command that changes a specific file representing your program counter. If it is not empty, you do something else.
So the program counter, the thing that tracks what line of code we are on, is just another file.
Everything is a file. The program counter is a file. The data is a file. The loop is a file. It is files all the way down.
That is just messy, but brilliant. It proves you can compute without the directory trick at all.
It is pure hackery. But the author wasn't done yet. There was one more criticism to address.
Proof number 3, hard mode. Why did they go back to Uncritty for this one?
Because of the criticism I mentioned earlier regarding Proof 1. Proof 1 used Regex back references. Those are too smart. Proof 2 used files 0 from, which involves streams. The author wanted to prove that the traversal logic of find itself, without fancy Regex copying and without stream manipulation, is Turing complete.
So find plus mkdir, but using dumb regex.
Specifically, awk-style regex, which does not support back references. You cannot say copy the thing you found and paste it. You can only say, does this match, yes or no.
But wait, if you cannot copy the state, how do you move to the next state? If I cannot read banana, how do I know to write apple?
This leads to the SEP trick. And this is the most technical part of the paper, but it is truly fascinating. They changed the separator between the words in the directory path. Instead of just a slash, they defined a separator named SEP.
And SEP is defined as a regex string that looks like, well, it looks like a typo. It is $, close parenthesis, question mark, open parenthesis.
$, close parenthesis, question mark, open parenthesis.
That looks like a syntax error, or like a cat walked on the keyboard.
It looks broken. The $, means end of string. The question mark means 0, or one of the previous thing.
So wait, if you put a $sign in the middle of a regex, shouldn't it just fail? It expects the string to end right there. If there's more text after the $sign, it shouldn't match.
Exactly. It creates a regex that looks like it shouldn't match anything. But here is the genius part. When you combine that specific broken-looking regex with the directory names they create, it forces the regex engine to align perfectly with the word being encoded.
Can you give me an analogy for that? How does a broken regex help us compute?
Think of it like a stencil or lock and key. Normally, a regex slides along a string looking for a match anywhere. By using the SEP trick, they force the regex to only click into place if the directory structure exactly matches a specific pattern. It effectively turns the presence or absence of a file into a Boolean logic gate.
Okay, so instead of reading the word, it tests the word.
Yes. They create marker files called T1, T2. If the regex matches a marker file, which only happens if the state aligns perfectly, it deletes that marker file.
And the deletion triggers the inventory.
Yep. They turn file exists into true and file deleted into action. They drive the state machine forward purely by checking if a file is there or not, without ever copying a string.
It is computation by presence.
Computation by existence. It proves find itself does the heavy lifting, not the regex engine.
So we have these 3 proofs, and they are incredible feats of engineering because we can. But let's step back and ask the big question for our audience of researchers and engineers. So what? Why should we care that find is Turing complete?
Aside from the sheer intellectual joy of it, the biggest implication is security. We often talk about weird machines and security.
Explain that term again. Weird machine.
A weird machine is what happens when you take a system designed for a simple task, like sending an email or searching for a file, and you exploit its features to make it run code it was not supposed to run.
Like a buffer overflow exploit.
Exactly. A buffer overflow turns a memory error into a weird machine. This paper shows Find is a weird machine out of the box. Think about shell-free environments. Sometimes system administrators give a user restricted access. They say you cannot use the shell, you cannot use Python, you can only run Find to manage your backup folder.
And the admin thinks they're safe because Find is just a search tool. What is the worst they can do? Find a file.
Correct. But this paper proves that if that user has a right access to a directory and they can run Find, they haven't been restricted at all. They can technically run any algorithm.
Right.
They can mine Bitcoin very, very slowly using just the file system.
They could write a virus in Find arguments.
Theoretically, yes. If you can compute, you can encrypt. You can decrypt. You can simulate logic. It breaks the assumption of containment. It is what security professionals call a living off the land binary, or LOLbin. You use the tools already there to do your dirty work.
That is terrifying. And also hilarious. It essentially means that any system with GNU find and write access is a general-purpose computer.
It highlights that complexity is hidden everywhere. We look at these standard utilities as simple, single-purpose tools. But modern software is so feature-rich, flags for regex, flags for execution, flags for streams, that they accidentally become programming languages.
It also makes me think about the resource model mentioned in the paper. We talked about infinite loops, but my hard drive is not infinite.
Right. The paper assumes an idealized file system with unlimited inodes and unlimited depth. In reality, your Find computer will crash when your disk fills up or the path gets too long.
So I cannot actually run a training run for a transformer model on my laptop using Find.
Not practically, no. It is like saying I can calculate digits of pi forever, but eventually you run out of paper. The math is still true, even if the paper supply is finite. The logic is sound. The physical implementation is just the bottleneck.
I love the joy of hackery aspect of this. It is taking the tools we take for granted and showing there's a whole universe inside them.
It is a reminder to read the man pages. Really read them. The author, Keigo Oka, found these possibilities just by looking at the flags and asking, what if I combine this with this?
What if I use execstar to create a directory inside the directory I am currently scanning? It is such a simple question with such a complex answer.
And that is where the best discoveries come from. Not always from building new things, but from truly understanding the things we already have.
So we have covered how directory recursion equals loops, how file paths equal state, and how flag abuse equals logic gates.
A completely valid computer made of nothing but folders and searches.
Before we sign off, I have to wonder. We focused on GNU find, that is the standard on Linux. What about the Mac users? What about the BSD find?
That is the final provocative thought. The paper mentions that BSD find and BusyBox find behave slightly differently regarding when they see a new directory.
So the infinite loop might not work?
It might not work out of the box. They might take a snapshot of the directory before they start walking, so they never see the new hallway you were building. But it raises the question, are those also Turing complete? Or is GNU find uniquely powerful because of its specific extensions, like files 0 from?
And what else?
Exactly. What other standard utilities are hiding universal computers inside them? We know awk is a language. But what about grep?
Grep is just for searching text.
Is it? If find is a computer, I wouldn't bet against grep. Or even tar.
A tar archive that computes its own compression. My brain hurts.
Keep exploring the depths of your man pages. You never know what weird machine you might activate.
Thanks for joining us for this deep dive on AI paper podcasts. If you enjoyed this look into the weird world of Turing completeness, hit subscribe and we will see you next time.